Hydrogen is the most abundant element on Earth. It really is nature's fuel.
We're at a very interesting stage of development of this technology where it's not quite ready for prime time, but it's getting tantalizingly close.
Fuel cell technology is evolving. The technology is improving constantly.
We're competing in a market that we have to compete with batteries and generators. And how do we do this?
I think hydrogen has great potential to become one of our primary fuels for the transportation industry in the future.
I would much rather drive my fuel cell vehicle than my gasoline vehicle.
Funding provided by the U.S. Department of Energy's National Energy Technology Laboratory, the Energy and Environmental Research Center's National Center for Hydrogen Technology, and the members of Prairie Public.
You've probably heard something about hydrogen. You may know hydrogen can be used to fuel cars. But did you know that hydrogen is used safely all around you every day? In data centers, warehouses, golf courses, and even breweries. Hydrogen is nature's fuel. It can be made where you want, when you want. Imagine living in a world without concerns about energy security or pollution, where you can get all the energy you need from domestic sources. Imagine the world of fuel cells using safe, clean, abundant hydrogen.
This is actually an electric car. It's got an electric motor in the front that drives the car forward, and it gets most of its electricity from a fuel cell system that converts hydrogen and oxygen from the air into electricity and water as a waste product. The concept of the fuel cell has been around 150 years as a sort of chemical principle. Starting about the 60s, these devices were made for space, and over about the last 15 years, automakers have been working very hard to develop the technology for automobiles as a way of simultaneously reducing the use of oil, reducing air pollution, and also reducing the release of greenhouse gases. This type of fuel cell is called a PEM fuel cell, proton exchange membrane. The way I like to explain it is sort of like a sandwich, where in the middle of the sandwich, the meat of the sandwich, if you will, you have a membrane material. You have hydrogen on one side, and you have platinum as a catalyst material. That catalyst allows the hydrogen molecule to split apart into protons and electrons. The protons go through the membrane, the electrons have to go around the membrane, and as those electrons are going around the membrane, they're powering the electric motor. Everything meets on the side with the oxygen and forms water as the waste product. Sometimes you'll hear it called a fuel cell stack, because a whole stack of these fuel cells. Just like you stack batteries together in a flashlight to build up more voltage. A car like this, you might have 400 fuel cells all stacked together to give you a few hundred volts.
Currently, we produce in the world over 50 million tons of hydrogen, with about a fifth of that being consumed in the United States. That hydrogen is being used primarily as a feedstock for making agricultural products such as fertilizer, and also a chemical feedstock to take the petroleum in its raw form and make it into the petroleum that we use in either diesel or gasoline. It's also used for medical applications, food processing, a variety of smaller type uses. If you look down the road in the hydrogen economy, some of those uses are for transportation, such as forklifts in a warehouse, or even putting electricity onto the grid. As always, when you start going into new markets, it becomes difficult for commercial companies to invest in something that's years out. That's why we have programs like the National Center for Hydrogen Technology, where you have some government support, because that federal support helps bridge that gap. With that, we work closely with commercial partners, and we find opportunities to provide developments in terms of being more effective, lower cost, better environmental advantages, and these are all things that are helping to buoy the hydrogen economy. As we go down this path and we get those goals met, we start grabbing more and more market opportunities. It becomes a matter of greatly reducing the cost of producing the hydrogen as well, the fuel cells, and also the end uses. And we then reach more and more applications, and we see it accelerating. And as that happens, you get the benefit of more public buy-in. The more they're familiar with technology, the more they want it and the more they're interested.
We see some very significant technological evolution taking place, which says that hydrogen can be exceptionally competitive. And we firmly believe that the ultimate energy source in this world is going to be hydrogen.
Hydrogen is interesting. It can be made a lot of different ways. There's a lot of domestic resources that can be used to make hydrogen. Any source of electricity can be used to make hydrogen from water. Hydrogen can also be made through a lot of biomass pathways. And right now it's made a lot from natural gas, which is not ultimately sustainable, but it's sort of a bridge technology to potentially getting to cleaner sources of hydrogen in the future.
To get hydrogen from water, we can use electricity to break the chemical bonds between oxygen and hydrogen. This process is called electrolysis.
Hydrogenics is a global leader in the development of fuel cells and on-site hydrogen generation. We can provide the hydrogen stations that produce the hydrogen. The process starts with the electrolyzer. That's where we make the hydrogen. We take city water and we purify it and put that inside our electrolyzers. From then, the water is electrolyzed. We produce hydrogen and oxygen. Oxygen is vented and hydrogen is captured. It is then purified through our dryer and purifier. The purifier removes any trace oxygen inside the hydrogen stream, and the dryer removes any moisture that was left over from the electrolysis process. The gas comes out at about 150 psi. From then on, it's compressed to 6,000 psi, where it's stored into storage tanks. From the storage tanks, the gas is diverted into the dispenser.
Most of the hydrogen we have today comes from natural gas through a process called steam methane reforming.
I would say about 90% of the world's hydrogen comes from fossil fuels, from reforming natural gas. For that, you need a capital cost of millions of dollars to create your plant, and you produce thousands of kilograms in one day.
We can get hydrogen from coal through gasification.
We've been using coal in this country for many, many years, and primarily it's been combusted. We burn the coal and we essentially convert it entirely to heat. In a gasification system, we convert coal to something very similar to natural gas. Then that natural gas has an extremely high hydrogen content, and we can then take that and either manipulate it to pure hydrogen, or we can even produce liquid fuels from it. Gasification has the promise of being one of the few sources that we can use to produce very, very large quantities of hydrogen. So as we transition to a hydrogen economy, coal is one of those domestic resources that can really step in.
We believe very strongly that coal must remain a part of our energy future. In order to do that, we have to find the technologies to utilize it more efficiently and effectively. We're convinced that because of our experience and knowledge that we've gained from our Dakota Gasification project, that we have a way in which to find a solution to this very challenging issue for our continued ability to utilize coal. Hydrogen today is something we look to for the future. If you want to talk about renewables, you've got to find a way in which to store the energy, because electrical energy has to be used at the time it's produced. And with renewables, you don't have that opportunity, because when the wind is blowing, you may not have the load. And so if you're producing it, how do we store it? The hydrogen concept is one of those opportunities.
Hydrogen generation can happen through a number of different routes. The easiest route would have us making electricity and then using that electricity to run an electrolyzer, which would split water electrochemically. We can also drive chemical processes which could then be used to produce fuels such as hydrogen or even liquid hydrocarbon fuels. Solar typically only works when the sun is up. Wind only works when the wind is blowing. If the sun goes down, then you have to make up all that solar power with other sources. Or if the wind is blowing and suddenly it stops, it causes instabilities. I need that power whenever there's a demand. The ability to store power is key to large-scale deployment because it removes that instability.
In the same way hydrogen stores the energy from the sun and wind, we can use hydrogen to store the energy in moving water.
Although hydrogen is the most abundant element in the universe, it's not readily available in a usable form. As a result, it has to be manufactured The good news about hydrogen is it can be manufactured in a variety of ways and with a large array of feedstocks. Liquid hydrogen in general first came to the United States as part of the space program, and there was large government support for that program to help subsidize the first plants. Linde is one of the world's largest industrial gas companies. Most of Linde's hydrogen comes from this plant here in Magog, Quebec. This plant utilizes a hydrogen waste stream that comes from a sodium chlorate plant across the street. That plant takes a brine, electrolyzes it, makes sodium chlorate and a 97% hydrogen waste stream. Linde captures that hydrogen stream and uses hydroelectric power to purify it and liquefy it for delivery across the country.
Essentially, the plant here uses electricity as the driving force to compress and liquefy the hydrogen. Our electricity, fortunately in Quebec, is essentially 97% comes from hydroelectricity, which is a renewable resource.
For green hydrogen, I'd say it's hydrogen that's produced with zero or minimal greenhouse gas or other pollutants as byproducts. Other renewable ways of making hydrogen is to capture solar, wind, wave, geothermal power, and electrolyze water to produce hydrogen.
We produce hydrogen in a very environmentally friendly way because of the fact that we have hydroelectric power. However, we have to transport that hydrogen, and the transportation does have an impact in terms of the carbon footprint.
The reason we liquefy hydrogen is it's perhaps the most efficient way to distribute hydrogen over long distances. And you can deliver the most hydrogen with the lowest carbon footprint as a liquid. Currently, there's three traditional ways of storing hydrogen, and it's largely dependent upon the volume of hydrogen you want to store and how far you want to transport it. So if you need a couple of kilograms of hydrogen, typically steel cylinders is what you would use. When we get to a few hundred kilograms of hydrogen, we look to employ stainless steel tube trailers. When you get to larger, maybe several hundred to several thousand kilograms of hydrogen consumption, that's where liquid hydrogen becomes highly economical. Beyond that is when you have to seriously start thinking about an on-site production. We know hydrogen can be delivered, compressed, and dispensed into vehicles very safely, as safely, if not more safely, than traditional fuels. Just as electricity is an energy carrier, so is hydrogen. Hydrogen is an excellent way to transport energy in a usable form that can be fed to a fuel cell and generate the electricity where you need it, when you need it. So whether you're moving your vehicles or you're lighting your house or heating your homes, one of the beauties of hydrogen will be it will provide a common energy currency throughout the world. In a hydrogen economy, every area of the world will be able to generate this currency with the resources available to it. Hydrogen is produced today in large scales at economies that would make sense for hydrogen fueling. So we're confident that industry can respond, and that is largely with the infrastructure, fueling stations that are fueling tens or hundreds of cars instead of thousands of cars. Obviously the infrastructure is very similar. What you need to fuel one car is pretty much the same equipment you need to fuel 100 cars or 1,000 cars.
When it comes to hydrogen refueling, there is quite a big difference. I'd rather fill at a hydrogen fueling station than a gasoline station, due to the fact that gasoline stations have been developed from the 1940s and 50s. Many of the standards and many of the safety concerns have been grandfathered in. When we look at development of standards, we're looking at what is safe to fuel with the knowledge that we know today, not from what we knew earlier. With this knowledge, we're able to ensure that we design fully safe hydrogen stations.
Cross Global is primarily an alternate fuel dispenser manufacturer. So that would encase propane, natural gas, hydrogen, and very soon liquefied natural gas. So we got quite a good head start in targeting from South America, Middle East, Europe, Asia. 80% of our business will be outside of North America. At Krauss, we're primarily an assembler and tester. Mainly the components come into our factory, assembled into sub-assemblies, and they move down the line to where they finally get put into the dispenser. You do some final wiring, tubing, moves on to the test bay. Every unit is tested fully, and once it's approved, out the door to the end customer.
When the public sees hydrogen at a station, they see the dispenser. They don't often see the storage or the compression or any of the other equipment that's very vital, but it's hidden from the public's point of view Hydrogen is about the vehicle that they're driving and the dispenser that they're filling it at.
To compare a hydrogen dispenser to a gasoline dispenser, you can't pump a gas. You have to move it on a basis of pressure differential. So instead of a pump that draws fluid out, you have valving that opens and closes to control the flow of gas to the vehicle. Instead of a turbine meter in a gasoline dispenser that spins to give you the reading on volume, you have a mass flow meter which senses the molecules of hydrogen flowing through it and gives you that same mass reading on the display.
One of the challenges with any new energy is distribution. In particular, the gasoline stations already exist. You're trying to compete with something that has been built up over 100 years. Initially, there will be hydrogen projects where buses return to a depot to fuel at night, or where you have the forklifts operating under one roof at a warehouse.
The biggest barrier right now is probably the lack of vehicles. Now, if you talk to an OEM vehicle manufacturer, they'll say the biggest barrier is a lack of stations. I'd say we're both right. It's a chicken and egg challenge. Do you bring out the vehicles first or do you bring the stations out first? Well, you need both.
You'll see reports that have suggested that it's going to cost up to $1 trillion to develop a new fueling infrastructure if we're going to deploy hydrogen in this country. The truth of the matter is that is totally wrong. The ERC has developed a technology called hydrogen on demand. And what it is we can use a wide variety of feedstocks which are readily available to produce hydrogen as you're filling your vehicle. No more than you need to fill it. Produces it on the spot in real time while you're filling the vehicle. It eliminates the cost of pressurizing the hydrogen, major cost out of the picture. Secondly, we eliminate the need for storage, another big cost out of the picture. Third key thing, we can use just about every existing gas station in this country for this technology, and you can drive up to that station, you can buy gasoline, you can buy an ethanol blend, you can buy diesel, you can buy hydrogen.
Well, our mission basically is to develop power systems that generate electricity because we firmly believe that electricity will be moving people around in the next wave of mobility for humankind.
In product development, like all companies in the clean energy space, we're trying to deliver on the three promises, which are energy security, environmental quality, and economic opportunity.
Nuvera got started by combining two emerging technologies. On one side, the hydrogen generation technology through reforming, and the fuel cell stack technology, the electrochemical device that converts hydrogen and oxygen into electricity.
POWERTAP is our on-site hydrogen generation product, which supplies on-site hydrogen to customers, forklifts, and fuel cell vehicles. The POWERTAP on-site hydrogen generator is designed to operate off of natural gas. We do this because it's a readily available fuel. There's over 2 million miles of pipeline within the United States going to 69 million customers today. We're using the same natural gas that you are in your home, running your boiler, running your hot water heater. Nothing is different. This box, we like to call it actually a hydrogen generation appliance. We've taken large-scale industrial process and intensified it. We have natural gas and city water come in on the utility side. It gets conditioned and then is sent to a steam methane reformer. It combines the steam as city water, combines the natural gas, and it breaks the bonds into a hydrogen-rich stream, which in the industry we call syngas. After that fuel processing, it goes to a purification step where we get high purity hydrogen, which is required for our fuel cell stacks. Within inside this canister is our steam methane reformer. It is taking the fuel and city water, it's converting the both into the syngas. We do sell these to both warehouses that are using forklift trucks, and also we're looking at opportunities to do merchant hydrogen, which is generating hydrogen for outright sale of the gas.
The hydrogen refueling system that we have developed is based on the reformation of natural gas reacting with water. There's a lot of critics of this approach because we're using a carbon-based fuel. While it's not totally carbon-free, it's an obvious choice as a part of the roadmap to carbon reduction.
The stack on top you see is a commercially available stack that goes into our POWEREDGE systems. These are systems that are provided to the material handling market as battery replacements. It's intended for industrial, kind of heavy-duty industrial applications. The real advantage of fuel cells over other power plant type technologies is they are inherently scalable. So if I need a stack of just 1 kilowatt, there it is. If I need this stack to be 90 kilowatts, I simply add cells to it. In terms of the prime power plant, the prime energy converter, it's real, it's today, we're doing it. They're ready, they're reliable, we're deploying them in fork trucks. The fork truck market is an ideal proving ground because it's a vehicle that's already electrified, it already uses batteries, and we're proving that the fuel cell has value in displacing batteries in that application.
This system is designed so that the user can push out the lead-acid battery, put in our system, and the truck doesn't know the difference. It's a hybrid system which has, instead of the gasoline-powered engine, we have a fuel cell engine, which actually is one of the nice points about fuel cells. With the growth of hybrid technology in over-the-road vehicles, you can very easily see how you could take the internal combustion engine out and put a fuel cell in. In the traditional power supply system for electric forklifts, you have big racks and racks of lead-acid batteries. For every truck, you have up to 3 batteries. And when the battery dies, you have to take it to a specialized machine that pulls the battery out, puts it up on a rack to be charged, and puts a new battery in. All this is very time intensive. A battery takes 8 hours to charge and 8 hours to cool. This system takes about 2 minutes to refuel. This is a fuel cell stack. This is what I call the dry end of the system, because there's no water. This is the wet end. There's a condenser here for managing heat and water. So as a fuel cell runs, it creates water. This manages the water to keep it from getting too high or too low, and also rejects the heat. Also in here we have the fuel handling components that take the very high pressure from the tank and step it down. There's an onboard computer which allows the fuel cell system to provide you with intelligent power. A lead-acid battery is just a dumb battery. It can't tell you anything about how healthy it is or how productive the operator is. And what it will do is it will just slowly drain down in performance over the course of the shift, just like a flashlight that's going dim. What you find with these is you'll have consistent power.
When you talk about family cars or SUVs, batteries will be too heavy and too bulky to be deployed and too expensive. To put a battery in a minivan today, you would have to add about 450 pounds. And that's carrying a gorilla inside your car. As an invisible gorilla, but nobody wants a gorilla in addition to the car you have. That's where the fuel cell will come in, and we'll have the right substitute in that case.
This is the world's first automated fuel cell assembly line. We can do 1,000 cells a day. Some of our stacks require about 50 cells. The reason for doing the line is, again, we're competing in a market that we have to compete with batteries and generators. And how do we do this? One of the things that we found in order to compete in a world market is we can't have exotic materials. We figured out how we could design this in such a way that we could build it with robotics that are the same as the auto industry, that are same in the computer industry. Not exotics, not the super titaniums, not the stuff that is just, that's very, very costly, high expenses, but we found low-cost materials that we could go ahead and put these together with. Everything that is readily available wherever we need to become a global competitor. What we're building today, we're actually finding those markets that we can go into. The telecom industry, the data centers, those backup supports that we need that would replace the battery or the generator. So right away, we're going to go ahead and drive to those newer markets. This happens to be a 1,000 watt system that we've created. This is a 5,000 watt system. We have communications. We can actually, from a remote distance, if the fuel gets to a certain level, we can go ahead and have this unit call the fuel provider and have them go ahead and say, hey, fuel's low, come and take care of it before the incident happens, before you start running this unit and all of a sudden you find out that you're out of fuel. And this is just conventional batteries that you see quite often in data centers, in telecom systems. Just like any common generator, it takes In some generators, it may take 2-3 minutes to come on. We can come on within about 5 seconds, 3 to 5 seconds. So we're instant. But in order not to lose that power, we bridge it with a small battery for a short period of time. I can demonstrate this. We turn on these really super bright lights here. And right now the fuel cell is armed and it's watching the grid. And it's intelligent enough to see if the grid starts to drop, the fuel cell knows that it's time to come on. As soon as we shut off the power, the grid is there, fuel cell's armed. Fuel cell immediately knew to come on because it lost the power. It no longer has any power, but you didn't see any blinks in the light whatsoever, not one. There's all kinds of opportunities that are open to what the fuel cell has to offer. It's open for the imagination. This is a 1,000-watt system right here. It's a unit that we can use outdoors. This is the one that actually Governor Schwarzenegger used to light his Christmas tree every year. Normally a 60-foot Christmas tree that had at one time 5,005-watt light bulbs on it and consumed about 25,000 watts of power. We were able to come back through, talk to them about that, change their way of looking at it, put LED lights on this unit, ended up dropping the consumption from 25,000 watts down to 450 watts, and we were able to use it with a small little 1,000-watt fuel cell system that we have here. So every year he delights in the fact that he's running a Christmas tree cost effectively and showing that there's other alternatives to power. This is green, and that's the great and wonderful thing about this is it's zero pollution, low noise, plus a tremendous amount of energy in a very small package. These are real. These are pieces of equipment we're going to see being used on a daily basis. Henry Ford, in his true wit that he had many years ago, he was confronted with stockholders and news reporters, and someone in the crowd said, you know, Mr. Ford, I know you're going to mass produce these things, but what are you going to do about the fuel? Where are you going to get the fuel for all these things? And he stopped for a second, he thought, and he said, you know, not going to worry about that. We know that, in fact, that hydrogen is everywhere. As long as we build cost-effective pieces of equipment that generate electricity, then we're going to look to those other companies that create and develop hydrogen to be able to supply us.
Cisco is an acronym. It stands for System and Services Company. We deal primarily with restaurants, schools, hospitals, anybody that's in the food service business. We use triple pallet jacks to move the groceries from our warehouse to the docks, and they're powered traditionally by lead core batteries. The fuel cell that we use here in Grand Rapids was provided for us by Plug Power, and they are used in place of batteries. And the fuel cell itself provides a consistent level of power during its entire use of its fuel, which is different from our traditional batteries, which have a declining performance. As soon as you start using that battery, the power starts to decline, and therefore the performance of the piece of equipment declines with the decreasing power. The traditional battery lasts anywhere from 6 to 8 hours, depending on how new that battery is, as compared to a fuel cell, which may last up to 14 hours per shift. Huge savings for us because we're not changing batteries, we're not recharging batteries, so we have utility savings as well. But also our selectors stay busy selecting groceries instead of swapping batteries out. They're a very smooth operating source of power. We've had good results from a handling standpoint. The units themselves weigh 600 pounds less than our previous batteries. And if you take the 600 pounds off, replace it with a new power cell, the handle, which the selector operates, becomes much easier to move around. And that's been an added benefit. The employees that operate the triple pallet jacks have been positive in their feedback about how they operate, how smooth they operate, and so far we've had no negative feedback from them, which is probably the most important vote of confidence. The people that actually use this day in, day out as part of their tools to do their job are enjoying the experience. The operators of these triple pallet jacks are responsible to fuel their unit when necessary. It operates much like a car does in terms of a fuel gauge. When it does indicate it needs to be refueled, the selector comes to the fuel station and goes through a very quick process, usually less than a minute, to refuel his or her particular triple pallet jack. There are warehouses using this technology to various degrees already. We're on the front end of this change. I'd like to think in the future this entire facility will be powered by an alternative fuel source. And if hydrogen is the answer, we're certainly one step forward in the right direction.
Our customers are asking for better solutions. They want to be quieter, they want to be lighter, they want to be smarter machines. Many of our products that are used for golf environments are in a situation where they're used very early in the morning. A lot of golf courses are being built around houses and they want quiet equipment. Fuel cells are a solution for this. We don't want to have to sacrifice performance in order to get the benefits of electric power. So first of all, one of our guiding principles is that the machines will be able to do the same tasks that you're used to and feel and operate much the same way. Given that assumption, there are some differences. The components are different sized and different weights, so you have to repackage them in new areas. They have to be weather protected and environmental protected. They're basically off-road equipment. The fuel cells that we are using are called a PEM fuel cell. PEM stands for proton exchange membrane, and it's one of several types of fuel cells, particularly suitable for mobile applications because they're compact, lightweight, they start up fast, and they follow loads very quickly. We've chosen to use compressed hydrogen as a fuel storage on board. In order to get enough volume of hydrogen, we are operating at 5,000 psi tanks. Keep the tanks lightweight instead of a thick, heavy-walled steel tank. We've got a composite tank. They're a bladder, either aluminum or some kind of plastic wrapped with threads to make the tank strong enough. We're able to get lightweight power, and we can refuel quickly with the hydrogen, where on batteries they're heavy and they take a lot of time to recharge. Hydrogen in a fuel cell is clean. It is completely green, and you give off water. There's a lot fewer moving parts than in an engine, a lot less friction. As the industry evolves, there's no reason it shouldn't be able to get long life as one of its better attributes. In my opinion, hydrogen is safe when used properly. The systems have to be designed so that they're safe, people have to be trained, then it's just like handling any of these other high energy contents. One of the key advantages that our industry has is that we are a fleet operation. Turf equipment on a golf course or a park system or something comes home to roost in the same building every night and then is deployed during the day and comes back. The ability to put in one central refueling site to take care of a bunch of product is inherent to our business. It lets us become, I think, a niche market that can start to use fuel cells quicker than many other places.
We got started in 1980, brewed our first batch of beer at a smaller facility. I was a home brewer who turned commercial brewer. Got 450 employees, 7th or 8th largest breweries in the country. Distribution in every state. I wanted to be more energy independent, and so we started looking at ways to both conserve energy and be more energy efficient. Actually, going back to when we first started, I put in things like ice banks to store energy at night, and so we've been embracing some of those concepts for a long time. We've done a lot of optimization and put in current technology, and some of those projects have 2 or 3 year payback, so it's not all done strictly for environmental benefit, but it's nice to get both. Some of the projects don't have great returns, and so you really couldn't justify them strictly on a return on investment basis. And we do a lot of what we do because we think it's the right thing, and as a manufacturer, being in an industry that does utilize a lot of resources, we see it as one of our obligations to do our business in a sound manner and look for ways to minimize inputs and to minimize waste streams. As a manufacturer, power needs are 24/7 because we have refrigeration and pumps and things that are operating. It was both from energy efficiency and from air emissions, I guess, that I really wanted to give the fuel cell a try. We've got 4 250 kilowatt units that are considered a direct fuel cell, so they don't need a separate source of hydrogen. They have an internal process that reforms the hydrogen out of the feed gas. So we feed it either biogas or natural gas, and the process is part of the fuel cell stack. And so as the gas goes in, the hydrogen gets separated, and then that's fed into the fuel cell. We also have heat recovery boilers. We capture about 1.25 million BTUs of energy back as steam, and that goes back into our brewing process. The fuel cell is, I think, at the top as far as overall conversion of that input energy to output electricity. Having the distributed power generation, you're not losing power through transmission line loss. If you can co-generate and use the heat and the electricity, you've picked up even more. So I think our overall efficiency is approaching 70% for our input energy with the heat recovery, which would be close to double, I think, what the average fossil fuel plant would be putting out. As far as nitrogen oxides and sulfur dioxide and other things that are normal combustion byproducts, none of those that are emitted from the fuel cell. All of our fermenters are tied into pipes where we can collect the carbon dioxide that's naturally produced from fermentation, and that's compressed and cleaned up and stored and allows us to have our own source of CO2 here. Normally breweries would purchase that if they don't recover it, and so now that we've recovered ours, we have our own source of naturally produced carbon dioxide that's been captured rather than emitted. Naturally produced carbon dioxide. It's used in the bottling process and moving beer around and dispensing beer. So we've just completed a pretty big solar array. I think we'll have one of the largest in the country. So that's pretty exciting, and we're using sort of new inverter technology that's very efficient. So we're doing a good job converting sun's energy into electricity. Middle part of the day we're drawing more power, so when our solar panels are putting out their maximum is when our power consumption is at its maximum as well. When the solar's not working, we have our fuel cells giving us our base load. So it's a good combination for us. Actually have our own herd of cattle. We feed our spent grain to the cattle, and the manure from that is composted and put back on our hops field. So we have a fairly closed loop on our hops here on site. We do treat all of our own wastewater. So we take all of our waste streams, our liquid waste from the brewing process, spilled beer, yeast, bits of hops and malt, and that's fed into a digester which produces between 35 to 70 cubic feet a minute of methane. And then that methane is fed to the fuel cells. We use a mix of biogas and natural gas. Since this is more efficient, it'll be cheaper to produce power this way. Up to close to 80% of our own electrical power needs generated here on site. Our goal will be to get to 100% power generation, and through both conservation efforts and some additional power generation, I think we can get there. I think it works for a lot of other industries. We get a lot of visitors here. I know there's quite a few hotels in one group that's put in fuel cells. One of the local casinos has put them in. So if you have a need for both heat and electricity on a continuous basis, you can justify this kind of technology.
The California Fuel Cell Partnership is a collaboration amongst industry and government. We have members from the automotive industry, energy companies, fuel cell technology companies, as well as government from state, local, and federal levels. We're working together to promote the commercialization of hydrogen-powered fuel cell vehicles.
Many years ago, when we were dealing with trying to reduce smog in the face of our continued population and vehicle growth here in California, we looked and said we really need to have zero-emission vehicles or something that's very, very close. And there were two technologies available. One was battery electric vehicles. The other technology was fuel cell vehicles.
With this particular vehicle, it actually has a hydrogen fuel cell system in it. And what that system is we have high pressure hydrogen stored in the vehicle. This fuel cell itself actually converts this electrochemically to electricity, which drives the vehicle. I tend to get comments about is the sound or lack of it. In this particular vehicle, this platform, we have a compressor which makes a little bit of noise, but overall it's about as quiet as it can be.
When we first started this program, we had a lot of vehicle issues and stuff like that. I have to say that we've definitely turned that around to where these vehicles are very reliable. We have them out in a fleet over the whole country, and we're very impressed with the way they perform and handle and their reliability.
Oftentimes I get comments about how stable it feels, how it doesn't feel like a prototype. It feels very much like a car they could just go out and buy, and obviously the next question I get is, why can't I get it now?
The most common comment I see is that the vehicle is really cool. When you get in the vehicle and you drive around in general, there's not much of a difference between that vehicle and a conventional vehicle. It drives about the same. Better pickup in the city, better acceleration, a little quieter. But when they know that it's boarding hydrogen and has a fuel cell, it has this cool green feel to it, and that's what people respond to.
We have real-world customers, so we'll have real-world feedback. The customer can cope with the infrastructure, with the vehicle durability, with range issues. The customers compares the vehicle just to a normal standard car. That's why we have custom operation, because it's not only important to have technology advancement, but also to listen closely to what the customer says, because at the end of the day, if the customer does not buy your nice piece of technical equipment, the whole technology is a failure.
With a battery electric vehicle, you have to make the electricity somehow to recharge the batteries. With this vehicle, you have to make the hydrogen somehow. The hydrogen tanks are right under the rear seats. The fuel cell system is located under the front seats, the driver and passenger seats. The electric motor is up front. And then in the back, under the cargo compartment, there's a battery. And the battery works with the fuel cell to provide electricity to the electric motor. The battery does the same thing that it does in a hybrid car, which is called regenerative braking. And what happens is when we're slowing down, the energy that otherwise would have just been wasted through the brakes is actually captured in the battery. And then when you need power to accelerate or go up a hill, both the battery and the fuel cell can put electric power to the electric motors. This vehicle is equipped with leak detectors that will immediately tell you if there's a leak, so you know to pull over, get the vehicle towed to a place it could be repaired. Hydrogen is very, very light, so if there is a leak, it tends to disperse very rapidly. The hydrogen storage tanks in these vehicles are incredibly well designed, very strong, fiber-wrapped cylinders. They've done extensive testing with them to ensure that they're as safe as possible. It has a neat safety feature where there's some little side pillars in the rear of the vehicle you can see, and there's tubes running up from the hydrogen tanks through those side pillars up to a pressure release valve, which is a little bump you see on the roof of the car. So if there's an accident, the system will detect a loss of pressure and the hydrogen will be immediately vented through the pressure release valve on the roof. You can measure hydrogen in terms of volume. You can talk about gallons or liters of hydrogen, but because the volume changes at different pressures, we tend to think of it in terms of weight. A certain amount of hydrogen is going to weigh the same regardless of what pressure it's at. 1 kilogram of hydrogen stores as much energy as 1 gallon of gasoline. This vehicle stores about 2 kilograms of hydrogen. Because it's under high pressure, that pump, when I clamped the nozzle onto the gas tank, it has to form a very tight seal. And unless the pump knows that there's a very tight seal, the pump won't even turn on. So it's got a lot of safety built into it. Right now, we're at a very interesting stage of development of this technology. In some ways, fuel cells are an easier fit for buses than they are for cars.
You don't get much cleaner than a fuel cell bus, that's for sure. It's a zero-emission vehicle. We're the first to actually build a fleet of fuel cell buses for an actual heavy-duty transit application. New Flyer Industries is the largest manufacturer in North America of heavy-duty transit vehicles. Currently have about 17,000 buses on the road at almost 250 different transit agencies. Because of the fact that we had the Vancouver Winter Olympics, there was a drive to showcase and demonstrate green technology. When the contract was originally tendered to do the fuel cell buses for the Olympics, we proceeded to develop an initial prototype which would eventually serve as the mold for our production. One of the big challenges with developing a fuel cell bus is to make sure that it can operate in the cold temperature environment. Once we were satisfied with that, then we proceeded with the production to build the 20 buses for the Vancouver 2010 Olympics. In most ways, the vehicle went through our standard production line, our standard production stations. The only difference was that there were a few extra steps at certain points in the line where we had to install the fuel tanks and some of the other hybrid components, but we were able to incorporate that all within our existing processes and equipment. Because we're a low floor design, which all our buses are nowadays for wheelchair accessibility and ease of getting on and off for passengers, one of the challenges with that is that the bus is very low to the ground, so there's no room under the bus to really install much equipment. With the large number of components that are required for the fuel cell bus, in terms of the hydrogen tanks, the batteries, the cooling systems, all of that takes up a lot of space. We ended up putting quite a few of the components on the roof of the vehicle, as well as in the rear engine compartment. From aesthetic standpoint, you would actually have a lot of trouble just from a quick glance telling a fuel cell bus apart from a regular bus. If you were to walk on and
sit in a seat, you wouldn't notice much out of the ordinary, and the stuff you don't see, which makes the technology interesting. The big challenge is operating a hydrogen fuel cell coach in cold weather. The primary byproduct of the chemical reaction is water. Of course, we run into the issue, what happens when you drop below 0 degrees Celsius? If you don't design for that, you can certainly run the risk of freezing that water, which can definitely damage portions of your fuel cell. One of the initial things we had to work on was a way to plug in the vehicles overnight to ensure that the fuel cell didn't freeze. The other big challenge is how do you ensure that on those cold days that you have enough heat available so that you can properly start the bus, and then once the bus is running, how do you ensure that you have enough heat available so that everybody is comfortable within the vehicle. One of the aspects about the fuel cell bus design is that it uses electric motors to drive the wheels. The fuel cell itself does not actually directly drive the vehicle. All it does is convert hydrogen to electricity. So that electricity is used to drive motors and other systems on the vehicle. One of the advantages of an electric motor is that at very low speeds, they generate a high amount of torque. The acceleration is very good. The other big advantage is the braking, because we have an electric system on the bus with very powerful storage batteries and generators. We're able to regain energy from the braking system when the vehicle stops. And not only does that increase the life of your brake pads and allow you to charge up your electrical system, but it also gives you a lot of stopping power.
Hydrogen buses are designed to work very similar to the way the diesel bus as far as duty cycle, and they're able to perform all the same functions as a standard diesel bus. Our buses have a range of about 300 to 325 miles. Diesel buses, and again this fuel cell bus. So depending on the route service, they can be out from anywhere from a tripper run, which is just a few hours, up to 16, 17, even 18 hours without any trouble.
These buses, because of extra infrastructure on the roof, for gas storage, for all the additional components, they're over 8,000 pounds heavier than the comparable diesel bus. But in spite of that, we're seeing as much as 100% or double the fuel economy over a diesel bus.
The main thing everybody notices is how quiet and smooth that the vehicle is in comparison to a standard diesel bus. There's no transmission on it, so it's very smooth, powers away very quietly. We have had some comments from riders that the bus is actually too quiet. It can actually sneak up on them. They've been surprised when it pulls up to the curb and they didn't even realize it was there.
With the fuel cell technology, this bus doesn't care where the hydrogen comes from. And the value of hydrogen in transportation applications is that we can make hydrogen from solar and wind and biomass. Here we're using natural gas. While it's not completely zero emission, it has some CO2 emissions. Well to wheel, it's still better than our regular diesel internal combustion engine vehicles.
They're basically a large golf cart. And there's not a lot of maintenance on a golf cart. One of the largest maintenance items for any bus is the brakes. And with these vehicles having regenerative braking, we're hoping to realize better brake life and then cost savings associated with that.
We're learning from these buses. We're learning from other examples throughout the world. All the supercomputers of the world, all the brilliant minds that delivered the technology in the first place can't think of every variable. And what we do here is we capture almost all the variables that they can't think of. And we're all learning from this, not just us as users, but the technology providers are seeing things that they couldn't replicate in the labs. We're very much committed to looking at alternative fuels to improve our environmental footprint. Zero emission from the tailpipe, virtually no noise from the engine, and the potential of addressing global warming, climate change issues, sustainable energy supplies to fuel our vehicles, to help us reach energy independence. Our end state goal is commercialization, so that all of the transit buses in the United States we would like to see as zero emission fuel cell buses.
Hydrogen has been used safely throughout our economy. We use most of the hydrogen today to make cleaner gasoline. But it's also used in food manufacturing and consumer products. If you look at hydrogen compared to gasoline, certainly both fuels have a lot of energy content. You must pay attention to safety considerations when using the fuel. Hydrogen is no less safe than gasoline, it's just different. If there is a hydrogen leak, it's very light, and so it will go up and rise immediately and dissipate into the atmosphere. It's totally non-toxic, it won't cause health problems or environmental problems if it is released into the atmosphere.
All vehicle fuels can be dangerous. If they weren't, they wouldn't be useful as fuel. The trick for any fuel is to engineer it so that it is as safe as currently available technologies. Today that's gasoline in conventional vehicles. And most people I know working with hydrogen believe that hydrogen is either as safe or safer than gasoline is today.
It is safer than gasoline. Most people say today that if you were to have a gasoline engine today and you were trying to bring it on the market for the very first time, there would be no way that you would be able to put that gasoline engine onto the marketplace. It just wouldn't happen.
I quite sincerely believe, and I've seen test evidence that supports my conclusion, that the gas tank in the Suburban that I drive is more dangerous than a hydrogen fuel tank.
We have conducted the 120,000 fuelings worldwide already. We know hydrogen can be delivered, compressed, and dispensed into vehicles very safely, as safely, if not more safely, than traditional fuels.
We've done extensive safety training with our maintenance and service personnel. We've worked with some very good partners that have designed some very good systems. Our fueling station, our facility upgrades all incorporate hydrogen sensors and fire sensors and very robust systems to track that.
Safety was a big part of it. I wanted to make sure that the testing that they had done was adequate for our employees' benefit, as well as for the community.
I have the good fortune to drive a fuel cell car on a regular basis, and I use it to take my kids to school, go to the baseball practice, go grocery shopping, come to work. When they fuel the car, there's no fumes or drips of gasoline. I would much rather drive my fuel cell vehicle than my gasoline vehicle.
Icelandic New Energy was founded in 1999. It's a joint venture company. It's owned 51% by Icelandic shareholders, which groups together the energy companies, the government, the academia like the university, the innovation center, investment funds and private investors. So all the key players in Iceland to have anything to do with hydrogen are joined into one company. And then we have Daimler, Shell Hydrogen and Statoil Hydro from Norway, which are the other three investors. And the goal of the company is to be a kind of an enabler to evaluate the possibility of creating the first hydrogen society in the world here in Iceland. They foresaw Iceland as a perfect test ground because they knew that all the energy sources to produce the hydrogen would be renewable, coming from hydro or geothermal. This ship is of course mainly a touristic boat, whale watching. On the ship you have 150 people traveling for 3 or 4 hours at the consecutive time. We put a fuel cell engine on a commercial boat. This is actually the fuel cell unit. The hydrogen storage is actually back in the engine room. So you have hydrogen pipelines coming in, connected to the fuel cell unit, and then we actually have a hybrid system, so we are also having a little bit of battery packs to have enough power for all the auxiliaries in the boat. There have been some technical hiccups on the way, but that's one of the reasons why you do projects like this, to learn how and which problems we're faced with taking hydrogen out to sea. There is now a project in Germany to build a ship powered solely by hydrogen. And they designed the ship around the hydrogen. What we did here is we basically put hydrogen on board an existing ship. And there are some complications with that. The main issue is how to get certification and how to fulfill all the strict regulation on having hydrogen on a ship. I think those have been the most important learning steps and teaches us a lot about how to do next steps regarding using hydrogen as part of a marine fuel. Usually when they go out for whale watching, when you see whales, they actually want to shut down the engine to get rid of the noise and get rid of the vibration of the ship. Before they had to run at least the auxiliary engine on diesel, so you still have some noise and some vibration. So what they do now is when they find whales, they actually can shut down the whole system. The only operation is the fuel cell, and that means no vibration, no noise and no emissions. And that's actually pretty cool when you're sitting in the middle of the Atlantic with absolutely no movement whatsoever, and you can see the whales peacefully.
I think people are very positive towards using the domestic energy sources to power everything we actually can. We are quite confident about the hydrogen infrastructure. We don't think that will be a hindrance or a barrier to a hydrogen society. People are very keen on what can we do, and they're realizing that the things we can actually do will also be clean. So that's a very big added benefit. But you also have to think about how much CO2 savings are in using hydrogen. It's all about the environment, and if we can also power the ship partly by hydrogen, which is in at least Iceland, a totally clean energy chain, that's of course a beautiful picture.
From power plants to wind turbines, city buses to lawn equipment, breweries to warehouses, hydrogen and fuel cells are quietly improving our ability to deliver clean, economical energy in our homes or cars and where we work. As the world's thirst for energy continues to grow and environmental costs mount, hydrogen provides us with the choice to create our own clean energy future.
Funding provided by the U.S. Department of Energy's National Energy Technology Laboratory, the Energy and Environmental Research Center's National Center for Hydrogen Technology, and the members of Prairie Public.